Chapter 2: Advanced Optoelectronic Devices. Types of solar cell. Main losses in solar cells. There are several types of losses in solar cells, which includes subband gate losses, lattice thermalization losses, junction losses, contact losses, and also recombination losses. Anti-reflection. This is one of the methods to reduce the losses in solar cell. The first one is AR coatings, anti-reflection coatings. A finished PV cell is coated with a material to reduce the amounts of the reflected light. This also can be seen clearly in our practical life, such as in our eyeglasses, sunglasses. Usually, this kind of technique is commonly used on a cell that is unsuitable for texturing. This method can reduce the reflection up to 5%. And the types of AR coatings for this kind of coatings of anti-reflection is including silicon nitride, silicon dioxide, and zinc oxide. This is an example of AR coating with the reflection percentage as a function of wavelength in micrometer. So as you can see here, this is the bare silicon surface without the AR coating. The reflection percentage is higher than 30%, and compared with these two with AR coating with a different reflective index of 2.3 and also 1.9. So for example here, the coating thickness is a lambda over 4, and which is around 600 nanometer here. So for 2.3, actually the reflection is less than 5%, around 3%. And also with a reflective index of 1.9, you can achieve up to 0%. It's too much different compared to the non-coating surface of the substrate itself. Another anti-reflection technique is texturing. This involves a manipulation of the surface of the substrate or layers. So for example, in this diagram, it shows that the structure of inverted pyramids. So these inverted pyramids is actually very substantial to reduce the reflection losses and also increase the absorption of the light probability in the devices because of this kind of structure. Texturing is formed by anisotropic etching, which is a method of etching of different crystal planes at different etching rates. So this kind of structure is actually reduces the total reflection by reflecting the light into the another pyramid instead of away. So this kind of reflection increases the chances of absorbing the light. 30% of reflection from polished silicon is reduced to 10% for textured silicon. This is another example of texturing. Such as shown before is the inverted pyramids. And you can also manipulate the surface into pyramids. This kind of pattern also reduces the reflectivity of the surface of wafers by forming of this manipulation of the microscopic structures. Bear in mind, this works mainly for single crystalline surfaces only. Silicon solar cells. This is a schematic of a classic dopant diffuse silicon homojunction solar cell. The top post, or the fronts, consists of the metal finger for contact. The blue color is the passivation. The red is the diffuse electron contact. The grayish color is the silicon. The green part is the diffuse hole contact, highly concentrated. And the back or the underneath is the metal back contact. So between these two, red and green, this red is the electrons generated in the textured p-type silicon via the phosphorus dot, whilst the green one is the aluminum doped regions, which is highly concentrated in holes. So this front surface is actually passivated with the hydrogenated amorphous silicon nitride, which also acts as passivation and also the anti-reflection coating simultaneously. And this aluminium as the back contact serves also as the reflector and a dopant source of during the firing. There is several techniques to increase the efficiency of silicon cells. First one is by selective front diffusions, as mentioned earlier. You guys are familiar with the diffusions region. Second one is the localized back contact and the dielectric back surface passivation itself. And of course, the third one is the metallization. So the first one, selective front diffusions. This technique is actually the first modification of the decoupling of the requirements of the diffuse region in terms of carrier collection and other hand high voltage and also provide good contacts. This region is actually very thin and moderately doped and surface passivated. This is to ensure a high quantum collection efficiency. A high dopant concentration is usually needed to guarantee a good contact formation by screen printing. A deep and highly doped diffusion is desirable to reduce the recombination and the fraction of the front surface contacted by the metal grain. Selective diffusion, also called a selective emitter technology, resolves this by trading off by picturing a low dop region between the metal fingers while creating a high doping level just below the fingers. Several approaches have been proposed for their fabrication such as structure, including selective diffusion, ion implantation, and also laser doping processes. The second technique is localized back contacts and dielectric back surface passivation. Aluminum doped regions helps to control recombination near the rear metal semiconductor surface. However, they are not ideal from the recombination or optical point of view. This level of recombination current ST can achieve is about to 1000 femtoampere centimeter squared. That is 10 to 50 times larger than a front phosphorus top region coated with a passivating dielectric, representing a limiting factor to silicon solar cell efficiency. Restricting the aluminium alloy P region for a small fraction for about 1 to 5% of the real surface while passivating the rest with an insulating material has a very significant electronic and optical benefits. In this approach, which is commonly referred as acronyms of PERC, which stands for passivated emitter and rear cell. PERL stands for passivated emitter, rear locally doped, or PERT, passivated emitter, rear totally diffused. 1,130 local contacts openings in industry, typically as lines, are made in the insulator using, for example, laser ablation. This approach is similar to so-called laser-fired contacts, where local openings are made after the final rear metallization. The third technique is the metallization. The screen-printed silver paste typically employed by industry need to be subjected to contact firing step. Besides ensuring a low contact resistance between the metal and the diffuse N-type region underneath, the conductivity of the printed lines improve during firing, but remains nevertheless higher than that of pure metal lines. This can be resolved, however, with the metal plating due to the improved line conductivity and the difference patterning technique. Narrower and taller lines can be fabricated, reducing these shading losses. Passivating rear contact that can withstand the contact firing process. Copper is often the metal of choice, offering attractive costs and advantages, of course. Another advantages of this approach that is circumvents the firing stability constraint for dielectric passivation layers. High performance firing free devices have been reported that exploit firing incompatible passivation approaches, such as the use of hydrogenated amorphous silicon as rear surface passivating film and hybrid devices featuring a homojunction front contact and a heterojunction rear contact. However, despite these developments, an important breakthrough with the direct industrial impact will be the development of the full area hole selective passive weighting rear contact that can withstand the contact firing process itself. That is all from me today. Thank you and have a good day.